we shall begin the end of chapter 23. So just a little expansion. I just want to point out that we have skipped around a tiny bit some of the synthesis considerations I brought in the previous mini lecture, and now we're just going to wrap things up with a look at other aromatic systems in a very cool kind of opposite to EAS. So other aromatic systems, those of you in ITR have already seen other aromatic systems, but let's do a little review as usual. Here is another aromatic system, a naphthalene system. All right, what's the product of bromination under the conditions of light? Well, that should make you scream. Radical reaction. And indeed, I would get bromination at the benzylic position because, of course, that is exactly where the most stable radical would form. Right there. Right there. There we go. Couldn't get a radical to form. Jeez, it's not as easy as I thought. But what happens when I do this under the conditions of bromine and this guy? Remember to recognize your reagents. This is a Lewis acid, an electron pair acceptor. So now we're talking, instead of a radical mechanism, we're talking about a polar mechanism, pluses and minuses. So that is going to give us electrophilic aromatic substitution. What do we get? Well, we get a mixture, not such a great mixture, probably 50-50, of these two orthobrominated naphthalenes. Why? Why, it's always the same. It's carbocation intermediate. It's the stability, the most stable carbocation intermediate is formed, as usual. And obviously there's not a para position open. Para is right there, and there's no hydrogen there. So that's not an option, but the two ortho positions would give you nicely delocalized carbocations that can ultimately get you to the important resonance contributor, that being the one that puts the positive charge right smack dab on the carbon bearing the electron donating group, in this case the methyl. So nothing new under the sun there. How about other heterocyclic aromatic systems? This is pyrrole, and as the book shows, and as you guys have seen, or like I said, you ITR types have seen, because you guys worked with thiophene, you can and should and must think of regiochemistry. Does my nucleophilic aromatic ring reach out and grab that electrophile and put it on that carbon, or does it go the other way and put it on that carbon? So that's position 2 or position 3, because the heteroatom is position 1. And the book seems to explain it as, well, they can both form. And it's true, they can both form. But there's definitely a more stable carbocation here. Now, you can certainly see that there's a good resonance contributor for the lower substitution, position 3. And that's all good and well. But you know what? There's more resonance contributors on top, because what you get would be positive charge delocalized there. Put my hydrogen there. And then the lone pair on my hydrogen can plop in right there. So I get more resonance contributors when my substitution takes place on carbon 2. Therefore, what we know is that this guy is the preferred intermediate, I should say. These guys are the preferred intermediate, more stable, and therefore the major product will end up being, just as you saw in ITR, substitution at position 2. So that you can see in looking at problem 23.63 in the back of the chapter. There's also some problems in the back of the chapter about pyridine, and pyridine is not going to be addressed in the same manner. So when you look at the carbocation intermediate from substitution on pyridine, keep in mind, think about orbitals. What orbital is that lone pair on nitrogen contained? And secondly, what orbital? And once you figure that out, can it delocalize that plus charge? Because if it can't, then it can't stabilize that plus charge. Well, hint, hint, it can't. And if you go back to hybridization and molecular orbital structures, then you will understand that that is an sp2 hybridized orbital that's containing the lone pair. And because it is 90 degrees opposite that p orbital that is the empty positive charge, no delocalization by that lone pair to be had. Okay, so pretty much the meat of the rest of the chapter is this swapo-changeo opposite thing, nucleophilic aromatic substitution, as opposed to electrophilic aromatic substitution. So all of what we've seen so far in 22 and 23, the aromatic ring has been electron-rich, the nucleophile. Sometimes aromatic rings aren't electron-rich. Sometimes they're electron-poor. So, as you can see, we've got lots of substituents on this aromatic ring pulling electron density away from it. And in fact, when we add what is obviously a nucleophile, the hydroxide anion, wow, we actually get substitution. What the heck is up with that? Another example of Carpenter lying to you. Well, sort of, kind of, not really. It's still not SN2, it's still not SN1, and unlike the Sandmeyer, it's still not a radical reaction. It's something brand new, and we are going to explain it in the form of dueling mechanisms. So, side by side, electrophilic aromatic substitution, nucleophilic aromatic substitution. In electrophilic aromatic substitution, what is the nucleophile? It's the aromatic ring. The more electron-rich it is, the faster the reaction goes. Just the opposite for nucleophilic aromatic substitution. It doesn't have much electron richness because it has these electron withdrawing groups on the aromatic ring that are pulling the electron density out of the ring. It is an electrophile. Okay, well, back to electrophilic aromatic substitution. Because it's the aromatic ring that's the nucleophile, it reacts with an electrophile. So, nucleophile, source of electron density, and we won't use that one, we'll use this one. Reaches right out and reacts with that electrophile. Nucleophilic aromatic substitution, on the other hand, as we've already said, this guy is my electrophile, so I need to add a nucleophile. And what is it going to do? Well, it has to find an electrophilic center to attack. And it makes sense that it would attack a carbon that is electron poor. And what we see is that it actually kicks a pair of pi electrons out of the aromatic system and onto a carbon. Whoa. So what I have here is a cationic intermediate. What I have here is an anionic intermediate. Cationic, anionic. Should make perfect sense since I'm adding something positively charged here and something negatively charged here. In both cases, these intermediates are stabilized by delocalization. Now we know the delocalization routine for the cation, but now we've got the same sort of electron movement that we've seen in the past that allows us to push the electrons around to make a more stable intermediate. And it's precisely because we've got this fantastic electron withdrawing group, the nitro group, that we could get this really quite stable intermediate. This is in fact called the Meisenheimer complex, and they can, in certain cases, actually be isolated. So, very similar mechanisms. In both cases, as always, the most stable intermediate is formed. The final step of the mechanism, what's going to happen? You want to go back down that energy hill all the way down to the aromatic, very, very stable aromatic compound. So in the case of our electrophilic aromatic substitution, that's going to be an E1 type mechanistic step to regenerate the aromatic ring. And what happens in our nucleophilic aromatic system is that anion slaps back down and kicks out a leaving group. So that step is also an elimination step. This is the step that we didn't cover much. Cont'd barely briefly mentions. It's called E1 CB for conjugate base. And basically what you can see is it's just doing what it needs to do. Regenerate the aromatic system, and instead of kicking out the nucleophile, it kicks out the leaving group. So, nucleophilic aromatic substitution, what you need to think about is when you have an electron poor aromatic ring, that's a requirement. It must have substituents on there that are electron poor. The other thing that you have to think about is, okay, here's my nucleophile. Where is it going to attack? Well, it's going to attack where there is a leaving group that could potentially be kicked out. In this particular example, we have two leaving groups that can be kicked out. So if it attacks the meta-chloro position, as shown on the left, then what do we have? Well, we have delocalization of the negative charge to this carbon. And we can delocalize that again. We'll see that we have delocalization on that carbon, but we can't get the negative charge into the nitro group, which is where we get the most stabilization. If we attack the para position, then we can get this guy, oh, not that guy, get this guy, put in all my arrows here. So here's our nitro group, here's our negative charge, and now we can get that extra stabilization that makes the whole intermediate more stable. So in this particular example, the nucleophile is going to attack the chlorine that is para, not meta, to the nitro group. And ultimately, our product will be substitution specifically right here, because the most stable intermediate is formed. Okay, one more substitution. This one's kind of wacky looking. Look at it carefully. One, I don't have a particularly electron poor or excuse me, electron rich aromatic, but geez, oh Pete, I'm very definitely adding a strong nucleophile. This does not have enough electron withdrawing groups on it to make it undergo nucleophilic aromatic substitution. But on the one hand, it kind of looks like that's what's happening, right? Because I could do this and get the anionic intermediate, and maybe that would work, But something's not right here. Because like I said, there's no electron withdrawing substituent on there to stabilize that anionic intermediate. And what's worse, how in God's green earth am I going to rationalize that the nitro group, the amino group, is para to the methyl? Something's going on here, something fishy. It would be really, really fishy. This is a mechanism that proceeds via something known as benzyne. Obviously, -ine, because there's a triple bond in the ring. And as you can imagine, trying to think about the pi orbitals overlapping to make that triple bond, extremely strained, extremely reactive, really doesn't want to be around. Therefore, as soon as that transient intermediate is formed, it will react with whatever nucleophile is present to immediately give either this intermediate or this intermediate and needless to say, either one of those anions will be protonated in a heartbeat by whatever conjugate acid is present, and conjugate acid is ammonia. So that's how you get benzyne, or that's how you get substitution with a really, really strong base. And you may think this is craziness, nobody would do this kind of chemistry, but you would be wrong, because here's an example not that long ago where these researchers carried out this reaction. They've got an aromatic furan on the left and this tetrasubstituted aromatic on the right at a very strong base. So that's a pretty big hint there. I mean, when you're looking at that base, you're thinking, I got to deprotonate something. Whew. There's no really strong acids present. But you know what? There is a weak acid present. And I generate a benzyne intermediate. And what the hey? This is wild. This is really wild chemistry. What's going on here? Diels-Alder. I am not making this up. It's true. These guys are your two Diels-Alder adducts. The gray, the gray box on the lower left kind of is a better depiction of showing you what this really looks like. Pretty strained, not the happiest molecule in the world, and you can treat that with HCl and water to break that very highly strained ether and that gets converted into these two regioisomeric phenols. Pretty amazingly cool stuff. Okay, so that's enough. We will wrap up. We have wrapped up chapter 23, everything you ever wanted to know about aromatics but were afraid to ask. And the next couple mini lectures will be all about cherry picking some really good review material out of chapter 26. So stay tuned.